basically, formally, in type theory, you have just types and nothing else. And each expression in type theory is, you call it a term, and each term has an associated type. So unlike set theory, where an element of a set can belong to multiple sets, for example, the empty set can belong to a lot of sets. That is not the case with type theory. So each term has a unique associated type. And so that's called the type of the term. And to write this formally, we use a colon. So if X is a term of type T, capital T, we write X colon T. And these are a few examples. I'll demonstrate a few more examples over here. So we have 0. Lean tells us that 0 is a natural number. It knows this internally. Natural numbers have been implemented in Lean, and that's why Lean knows this. If we check true, it should tell me it's a Boolean, but it's not telling me that. Oh wait, it is. I don't know what this is. Give me a minute. Messages. Yeah, true is a Boolean. And if I check this expression over here, it should tell me that it's a natural number, and it does. This is similar to the type inference that I was talking about earlier. And some expression like this involving Booleans is also a Boolean. So that's essentially how it works. As I mentioned earlier, everything in type theory has a type. So we saw that 0 has the type natural numbers, but then natural numbers, the type of natural numbers is also a type, and it's also an expression in type theory. So it should have an associated type. And if we check, Lean says that it has type with a capital T. So this begs the question, what type does type itself have? And we see that it has type 1. And if we ask what type 1 has, it has type 2. And you can see how this continues. That's basically how it works. And this hierarchy is not cumulative, in that natural numbers belong to type, but not type 1, nor type 2, or anything else. That's how it works. I won't be speaking much about universes for the rest of the talk. Yeah. So we've seen. Yeah, go on.
Is there a notion of subtype?
I mean, sort of, but not really. So what we do instead is coercion. So you're talking about 0, like interpreting 0 as an integer instead of a natural number, right? Something of that sort.
Basically.
Yeah. So there is something called a subtype, but it's not a fundamental thing. It's more like an ad hoc thing. Instead, what we do is coercion. So we can have a symbol representing multiple types. Like 0, for instance, can be a natural number, an integer, a rational number, or some 0 element of some group. And what we do is, like, by default, it's a natural number, but we can coerce the type. So I will demonstrate that over here. So if I say 0 int instead of nat, it tells me that 0 is an integer. So it's reinterpreting the same symbol differently.
I see.
So yeah, this is how you coerce.
Okay.
Yeah, cool.
Hello. So
Yeah.
is there any reason why this non-cumulation of hierarchy is useful?
Not that I know of. Like, so a lot of systems actually use cumulative hierarchies. I'm not sure why, like the design choices behind this.
Okay, thanks.
You said
Yeah,
the type of a certain thing is unique, right?
Yeah.
So, like, doesn't that make sense? Because so if, for example, the nat thing belongs, that thing is of type, right? And you said type is of type 1. So cumulative.
Oh, so you're saying you're saying a good answer to this would be like the uniqueness of the type. Oh yeah, that does make sense.
Yeah. Thanks. That's a nice idea.
Cool. So we basically, till now we've seen what types are and how they work. Now we'll look at an example of how you can build types. Wait, did my entire screen turn orange for you people?
No.
Wait. I have this nightlight sort of thing. I'll disable it before continuing. I don't know how it works. Yeah, I don't know where it is. Never mind, I'll continue. It's still readable.
Wait, 1 second. Before we continue,
yeah,
or maybe we can do this at the end. I don't know about the answer that we arrived at for why it's not cumulative. That doesn't seem like the right answer, right? Because we just talked about coercing a type. So
Oh, coercing is basically I don't know, a programmer hack, I guess. Like, so you use the same symbol to represent multiple things.
is that not formally part of type theory itself? It's more of a
Yeah,
other
it's more
thing.
of a programmer hack kind of thing. Like, yeah, we speak of zero as a we like in we want the same symbol to mean different things in different contexts, and that's why coercion is a means of achieving that. Like, it's not a
So
formal part of type theory.
it's kind
So
of like a
type is a
right version. It's like a relabeling of sorts.
Yes, it's sort of like a yeah. You interpret it differently. Yeah, reinterpretation, I guess. Yeah.
it's a type is a local property kind of thing. Like it depends on what you're working on or where you're working, essentially.
No, so type is a global property. So if I type zero ignore the unintended pun. Yeah. So, but if I type zero by default, it's interpreted as a natural number. But if I like, so what a mathematician would do if, if you were like implementing this formally in some system, maybe you would label things with a subscript. So, for example, zero subscript n to denote the zero of natural numbers, and so on, like zero of z. But in practice, this is very tedious, so that's why we use coercion. So, but zero by default is a natural number, like it's a global property, like it doesn't depend on the context or anything. It is always a yeah.
Cool.
Yeah. Thanks for the questions, though. Yeah, so we can also build functions. So we've seen this in some form already in the context of the lambda calculus that I described. So basically, it's the same thing. So you can apply one function to the other. So if you have a function from alpha to beta, and you have a term of type alpha, you can apply it to get a term of type beta. And yeah, building functions, I've described it over here. So let's say you have a type alpha and another type beta, and given some arbitrary term x of alpha, if you can construct a term t of type beta by temporarily assuming x, then you can essentially build a function which takes in x and outputs the value. So here's an example of what I mean. I take a natural number n, and by temporarily assuming this value, I can construct another value, n plus 2. I'm adding 2 to the natural number. And this entire thing, the function that takes a number n to n plus 2, is represented with this syntax in lean. So lambda is for historical reasons, the lambda calculus. And this is lean zone syntax, like the whatever, the equal to arrow thing. And this is how it's seen. Yeah, so I mean, there's not a lot to this. I could say that this function over here is equivalent to nat.add2. So the reason I bring this up is that normally we see addition as a binary operation, which means that it takes two numbers and returns another number. But what we're seeing here with nat.add2 is actually a partially applied function. When we check the type of this thing, we see that it's a function that takes in a natural number and gives out another natural number. So it's not a fully applied function yet. It's a partially applied function which takes in a number and adds 2 to it. So this is this has historical relevance because one can stick to a minimal framework in which every function takes only a single input, and this can be done without compromising on any generality of any sort. So this is good enough to suit all purposes. So this is the style that's usually adopted in practical implementations of lambda calculus, so Haskell and so on. So yeah, that's basically it. Yeah, so I another quick point that I want to make is that these alpha and beta don't need to be like primitive types like natural numbers. You can have weird types like the type taking basically you can take a function from naturals to naturals and also construct a type from that space to the space of naturals. So you can do all sorts of things like this. It's not restrictive in any way. Yeah, and all the properties of natural numbers are quite obvious. So yeah, there's not much to add over here. At this point, I'll take a quick detour and I'll start speaking about logic instead of functions as we were talking about. Uh, so I'll also it's not just any kind of logic. It's actually a special variant known as constructive logic. So what we're used to is what's called classical logic. But constructive logic differs from this in that we don't really use the law of excluded middle anywhere over here. So law of excluded middle says that for any proposition P, either P is true or the negation of P is true. So constructive mathematicians don't really view that as a valid viewpoint. So these are not, this principle is not used anywhere in proofs. And when we say that we have proved something, we usually want to have a witness of that proof. So basically, we are saying that we want to actually construct things without proving things indirectly. Don't basically yeah. I won't say more about constructive logic. Now we'll just directly dive in. Before that, are there any questions about functions or things like that in general?
Yeah, I think I missed something you said. You said something like the types, the terms need not be of predefined types like natural numbers. And then you said,
Oh, okay. Oh yeah. I just said yeah. They don't have to be like simple types. Basically, I mean, this is not a technical term. All I'm saying is that they don't have to be things like natural numbers over here. Like when you're constructing this arrow thing, it's between the space of all functions from natural numbers to natural numbers, and it outputs a natural number. So in summary, what I'm saying is that you can construct these between arbitrary types. So this is the type of all functions from natural numbers to natural numbers. And you can take a function from this space and also map it to some other thing. So you don't have to work with like Booleans or natural numbers. You can work with all sorts of composite types. So you can have n arrow, and yeah, you can have all sorts of weird things like this.
Okay, cool.
Yeah.
All right. Thanks.
When you wrote that nat.add2, you said it's some partial function or whatever. What does that mean?
Partially applied function. So if we look at nat.add, so what we see is that it's a function that takes in a natural number and gives out, so the brackets should be over here. I hope you can see my cursor. So basically what it says is that nat.add is a function which takes in a natural number first, and as output it gives out a function which takes in a natural number and gives out a natural number. So it's a function from n to n to n.
So the second our input is the thing you're adding, right? Like for example, you added 2, so that's the second input, is it?
The first, so when I do nat.add2, what I get is actually a function now from natural numbers to natural numbers. And if I give this function nat.add2 is a function from naturals to naturals. And if I give this some input, it'll evaluate to 6. I mean, if I reduce this, so I get 6.
Okay.
So we're basically applying it step by step instead of giving all the arguments at once.
All right.
Yeah, so nat.add2 is just a partially applied function, which, yeah, it's just a partially applied function which adds 2 to its input. Yeah. So
just so not about types, but about constructive logic. So when you said that proofs are constructive, did you mean that the proofs by contradiction and those techniques are just not valid?
Exactly. Yeah. Proof by contradiction is not a valid technique. There is something weaker, which is proof by negation. And when mathematicians talk about proof by contradiction, half the time they're actually using proof by negation. I might say a few more things about this later on, or like we can discuss this after the thing.
Sure.
But yeah, it's a good point. Yeah. You don't use proof by contradiction. But yeah, I will illustrate proof by negation once I've covered negation.
Cool. Thanks.
Yeah. Cool. So yeah, we'll dive in. So the first logical connective that I want to talk about is implication. You'll see why in a minute. So implication, so what I'm going to say will sound slightly different from what you're used to, but it won't be too different. So you'll still be able to relate it with what you already know, the classical mathematics. So with implication, let's say I have two propositions, P and Q. Let's say we know that P implies Q. And additionally, let's say we also know that P is true. With these two facts, we can conclude that Q is true. And this is what's called as modus ponens in the language of logic. So And another thing, if we can temporarily assume P and then derive Q, then we say that we have a proof of P implies Q. Yeah. So does what I've said so far ring any bells? Like, do you see any connections with anything else I've mentioned in the talk so far?
The
Functions.
partial
Yeah.
function business.
Yeah, functions. Yeah, basically. Yeah, exactly. So the cool thing is that, so you can word it slightly differently, and the cool thing is that implication and functions are essentially the same thing in type theory. So I'll state this more rigorously. So let's say P and Q are propositions, but instead of propositions, I'll call them types this time. So P and Q are types, and let's say we know that P is true. Instead of saying P is true, I'll say we know that there's some P colon P. So we have that type is inhabited essentially. So there is some element of that type. And let's say we also know that P implies Q. So in my different wording, I know that there's a function from the type P to Q, and it's called F. So we have this function F from P to Q. So the type P implies Q is inhabited. And now you can construct a term of type Q. Essentially, you can show that Q is also inhabited by just F of P. So F of P. F is this thing over here. P implies Q. P is this proof of P. And by applying one to the other, you get a term of type Q, which is under a new interpretation, a proof of Q. So yeah, that is the connection and the counterpart to this. So this was applying functions, now creating new functions. Let's say we have Q of type capital Q. I really should have chosen something else. Yeah. So let's say we have Q of type capital Q, and we can derive this by temporarily assuming P of type capital P. With these two facts, we can construct a function from basically we can construct this function, and if we check the type of this function, it'll have type P implies Q. So in other words, if we can construct Q, we can show that we can prove Q by temporarily assuming P, then we can produce a proof of P implies Q. So this is a very deep connection between mathematics and logic, and it goes by the name of the Curry-Howard correspondence. So this was something that was discovered independently by Haskell Curry.
Could you go to the previous one?
Yeah.
Yeah. So why is P colon P a proof of proposition?
Oh, that's just the way we interpret things. So you can read this thing in two different ways. So maybe I'll start. Maybe I'll type it over here. So yeah, you can interpret it in two different ways. So if I have, I'll just type out all the things. Yeah, I hope this is still visible. It's kind of faint. So yeah, under one, so you can read the same thing, but with two different frames of mind. So in the first frame of mind, we read that we have a term P of type capital P, and we have a function from, we say that P and Q are two types. So we have a function from type P to Q. And if we look at F of P, then this has type Q in the regular type theory interpretation of it. So this is how you read it in the type framework. Now this is the exact same thing. I won't type a thing now. So we'll read this differently. So we interpret this to mean that P is a proof of proposition capital P. So P and Q are propositions now instead of types. And we have a proof of proposition P. That proof is called lowercase p. And we read functions as implication. So we look at the proposition P implies Q. We're saying we have a proof of P implies Q, and the proof is called F. And now we also say that we have a proof of Q, and the name of this proof is F of P. So this is the proof that you get by applying F to P. So this is modus ponens essentially. Yeah. So it's essentially different readings of the same thing.
So you're imagining the proposition to be a type itself.
Exactly. And another detail that I don't think I mentioned was that every just how types like natural numbers have type, propositions in type theory have type prop. So yeah, there's this hierarchy. So prop is the universe, and P and Q are types in this universe, and lowercase p and lowercase q are terms of the respective types.
Wait,
And
no, so wait. So in this case, proposition has type prop, and proposition itself is a type.
proposition,
Because
you mean
if
P has type prop? Capital
So-
P has type prop.
yeah, so capital P has type prop. Then what does
Huh.
P:(P mean? That it has.
P:(P means that the type P is inhabited. That means you're looking at the type. So prop is the universe.
Right.
You have the type capital P in prop, and you're saying that within capital P is a type essentially. So capital P is a type within this universe, and you're saying this type is inhabited.
Okay.
There's a member of this type. So yeah, P:(P means that you have a member, and then all these things that I said earlier. And with another reading, you can imagine this to be implication. And yeah.
So if I go
So
like type
go on.
nat 0 is the same as going prop P small p.
Exactly. Yes, you've got it right.
ठीक. Weird.
I know, but it's very cool. Like you can encode
That's
logic.
cool, yeah.
Yeah, you can encode logic within this framework. Right. So as I said, this is called the Curry-Howard correspondence, and it's not restricted to just implication and functions. It turns out to run a lot more deep than this. So we'll see that you can express for all and there exists and all these things within this framework. So the next thing I want to talk about is, oh wait, yeah, I forgot this. So this is a nice mnemonic. So PAT stands for propositions as types, and it also stands for proof systems. So you interpret every proposition as a type, and a proof is basically a term of that type. And yeah, that's the interpretation that you need to keep in mind. So that way you can leverage the framework of type theory to do all your math and proofs and so on. So yeah, it's a very nice duality.
Sorry, so I think I paused, like something happened in the middle. I just had a question. You said small p is of term capital P, right? Or you
Is a
said
term of type capital P. Yeah.
right. So
So
and
if
you
it
said
helps, you can replace this. Sorry.
you said that small p is a proof of capital P.
Yeah.
Right. So the proof of a proposition is of the type proposition.
Exactly. Yeah. So that's what I mentioned earlier. So the good thing for bringing this up, because essentially, if you have a term lying out in the wild, you just need to check its type to see if it's a valid proof of the proposition. So
Okay.
yeah. So this is what I was talking about earlier. Yeah. Thanks for bringing it up.
All right.
Yeah. So yeah, that's how you can use type checking to do proof checking or proof verification. So yeah. So again, conjunction, as you would expect, a term of type P and Q is constructed by first taking a term of type P and a term of type Q and combining them together into P and Q. So that's how we interpret and. What would be the corresponding the type version of it? So just how functions was the type version of implication. What do you think the type version of and would be? Think in terms of sets, if that helps. I mean, even a wild guess will work. Like, let's say P and Q are sets. You want to construct some term which is built from P and Q.
Some composition of a function, maybe.
Not quite, but I think you're close. I mean, yeah, keep thinking along these lines. So think in terms of sets and the kind of operations you can do on sets. Like you can build a lot of stuff in set theory. Like you can take the power set, you can take you can basically take products and so on. Wait, was someone saying something?
Did you answer the conjunction thing?
Oh no, I didn't.
Oh, okay, fine. Sorry.
I mean, even a wild guess will work. I mean, what does your intuition tell you?
I mean, intersection is the first thing that comes to mind, but
Okay,
that
that is a good point. So it's not quite intersection. So, I mean, okay, yeah, I think there are a lot of possible answers for this. So maybe I'll just give it away. So the answer is the product of two sets or two types. So I haven't defined this yet, but it's basically so think of this in terms of set theory. So if you imagine P and Q to be sets, then to construct a term of type P cross Q, the Cartesian product of P and Q, what you need to do is construct an ordered pair where the first term is of type P and the second term is of type Q, and then you have a term of type P and Q. Sorry, a P cross Q, where cross is the Cartesian product. And this is exactly how you would construct a term of type AND. So you say P and Q if you have a proof of P and you have a proof of Q. Does that make? Oh no, sorry. I think my computer might slow down. Yeah, but does that make sense? I'll also show the corresponding lean thing. Hopefully that will make things more clear.
Wait, could you just tell me how you define P cross Q again?
So think of this completely intuitively. Like you don't need to worry about the the implementation and so on now. So P cross Q in set theory. So P cross Q is basically the set of all ordered pairs where the first term is from P and the second term is from Q. So to construct something that is an ordered pair with the first coordinate P and the second coordinate Q, you can do this by taking a term of type P and taking another term of type Q and putting them together.
All right. So this is my question. Does the order matter? Because so typically in conjunction, P and Q, Q and P are the same. But
yeah. So
P
the order
cross
does matter.
Q cross P are not the same, right? So I wanted to know if you look at them as the same type, as in if you look at the type P cross Q and the type Q cross P as the same thing, because in our normal logic, P and Q, Q and P, we look at them the same way.
Yeah, that's a good point. So the thing is here, P cross Q and Q cross P are different, but you can show that you can construct a function from P cross Q to Q cross P and vice versa. So they are equivalent essentially. So
right, yeah.
So that's how you settle this thing in constructive logic. So these are different types, like you pointed out, but yeah, they can be identified, like via implication, by implication.
So
yeah.
This I was gonna ask a question, kind of like you said P cross Q and Q cross P are the same type. Is that type 1, or so is it type or is it something else?
Wait, could you come again? P cross. Wait. So
what is the type of
P
cross Q basically?
What is the type of P cross Q? Good question. So that depends on the types of alpha and beta. That depends on the types of P and Q. So I was reading this thing over here, so that's why I said alpha and beta. So that depends on the types of alpha and beta. And to answer this fully, I would have to go into universes. The technical answer is that it's a maximum of the two universes, but that's not helpful. If we consider everything to be a type, then it will have type. So if we build this weaker version of prod, then the result will have type. Where A and B are just plain types. So, but yeah, this like fully answering this question will need technical details of universes and so on. But I think it can still be understood intuitively, like without universes.
But P cross Q and Q cross P, do they have the same type at least, even though not the same object as such?
Yeah, they have the same type. Yeah.
Okay. All right.
Is there any reason why we are not using intersections here?
Because so in set theory, you can define an intersection using logic. So you define the intersection of two sets to be the set. You use comprehension and you say X in P and X in Q, and you use comprehension to define the intersection.
Right.
The thing is over here, you don't have any logic to begin with. Like so, you just have these rules for building new types. That's all you can do. So That's why we don't have a notion of intersection of types as of now. So that's why we have to yeah,
Can't we
basically
use something like some Boolean thing, like which kind of like something like if that element is present in both of the sets, like if it's true for both P and Q, then it lies in their intersection, as we might call it. Like, can't that be constructed?
no. So another point here is that if you have, so you can't have common elements between types. So as I mentioned,
Right,
every term
right,
has a
right,
unique
right,
type.
right,
So
right.
that's another issue over here. So
Right, makes
yeah,
sense. Thanks.
instead what we do is, yeah, so this is, if you want the implementation, this is how it looks. I won't be spending too much time on this. You can ignore the word inductive, like it's not supposed to make sense at this point. Basically what you're saying is that to construct a term of type and PQ, you type intro and you give it a term of type you give it a term lowercase p of type capital P, as well as a term lowercase q of capital Q. And what you get as a result is a term of type and PQ. Oh wait, I've written an example over here. Hopefully this clarifies things a bit. So basically I'm saying that P and Q are propositions. P is a proof of capital P, Q is a proof of capital Q. And what we want to construct, this thing after the colon over here, is a term of type and PQ. Basically, we want to prove that P and Q is true. So to do this, what I do is and.intro. So this is and. This is the intro constructor of and. So again, like technical details aren't very necessary over here. So and.intro, I first supply P, and then I supply Q. And what I get as a result is something that has type and PQ. That's how it works. I'll speak more about inductive types and what all this means in more depth later on. But this is roughly how it works. Is conjunction win? If it is, then I'll move on to disjunction.
So P and Q is basically P cross Q, right?
Yes.
Why do we have two different notations?
Oh, we don't need to have two different notations. That's the point. Like, so these are essentially the same thing. Like you can write instead of like instead what you can do is instead of manually writing and, you can write prod everywhere. And whenever you read prod in the context of propositions, you just mentally rewrite it as and. So you could do that, but this makes it easier to read things in practice.
Okay.
Yeah, they're essentially the same thing. Isomorphic up to relabeling. So prod instead of and, intro instead of make. But yeah, they're essentially the same thing. You don't need two things essentially.
Right.
I don't know if I missed this. What's the type of a proposition?
The type of a proposition, yeah, it's prop. So it's called prop.
Oh, okay.
Yeah, this is the universe in which all propositions live.
And P cross Q is just a formal construction of like an ordered pair.
Exactly. So you
It's
put it
nothing
well.
more.
Exactly.
So P cross Q itself is not a proposition.
P cross Q itself, that depends on the types of P and Q. If P and Q are propositions, then P cross Q will be a proposition. If these are not propositions, if these are arbitrary types, then it'll have some other type. So it'll have type. I mean, in some restricted case, in the answer that I gave to Karthik.
Yes. Right. And is there a case when like proofs are propositions or they just?
No. I don't think there is a case, because if you're saying a proof is a proposition, then a proof itself must be a type of another proposition. So you have a proposition which is the type of a proposition, and yeah. So yeah, that doesn't happen.
Okay, fine.
Yeah.
Fine.
Yeah. Right. I don't know if I mentioned this already, but and.intro is a term that has type and PQ. And this is what I said earlier about Lean being smart enough to infer things from context. So I haven't mentioned capital P or capital Q anywhere, yet it has enough information with it to infer these types automatically and figure out what to insert. Basically figure out what type this thing is. Right. So disjunction is a little more complicated. Not too much though. So basically, when we say that P or Q is true, what we want to do is produce either a proof of P or a proof of Q. And we additionally, we want to also remember where this thing came from. So this is something that's not done in classical logic, but this is something that we do in constructive logic. But yeah, it's not too much of a difference. It's just a different way of looking at things. So again, this was hard to guess, so I decided to just give it away. So is everyone familiar with the notion of a disjoint sum of sets, like in the context of set theory?
No, I don't know. Sorry.
Yeah, that's okay. So yeah, let's say A and B are let's say A and B are sets. So disjoint sum is basically a way to, maybe I'll just write it out. Yeah. So first, what you do is you construct. I'm mixing up type theory and set theory notations, but wait, maybe I'll change to a different theme. This is barely visible. This is barely visible. Give me a minute. So right. First you build this set, which is basically you add a tag to every element of A, saying that it comes from set capital A, and you also construct this set, which is the same thing except for B. So B, capital B. So you construct these two sets, and then you take the regular union, the set theoretic union. So any element of this disjoint sum or disjoint union will basically be an ordered pair, where the first coordinate is some term A or element A, which is a member of the set capital A, and capital A is the second coordinate over here. So that's essentially how a disjoint sum is. You're taking the union of the two things while keeping track of which thing comes from where. So yeah, that's basically a disjoint union. And under the Curry-Howard correspondence, union and disjoint sum and conjunction or OR are the same thing. So if you want to see the implementation of it, it's basically this. I'll switch back to my old theme. So yeah, if you want to see the implementation of it, this is basically it. I won't dive too much into it, but all it says is that if you want to construct a proof of P or Q, and you already have a proof of P with you, then you can use this INL constructor, introduction left, that's what it stands for. You can use this INL constructor and give it a term of type capital P to produce a term of type P or Q. And likewise, if you have a proof of Q, you can use this INR constructor to basically produce a proof of P or Q. And like Arjun pointed out earlier, or PQ is not the same as or QP, but these are, you can go from one to the other. You can construct a function that takes a term of this type to the other type. And yeah, that's how we deal with that. Yeah, so the conjunction is a lot cooler than disjunction. Like disjunction is kind of lame. So apart from disjunction, so yeah, here are a few examples. So if I want to construct a term of type some alpha beta, and I have a proof of alpha with me, I use the left introduction to introduce a proof of some alpha beta. So the cool thing is that since it's expecting a term of type some alpha beta, I don't need to explicitly mention beta over here in this term. So it can infer it from the context. So this is again an advantage of type theory. And likewise, I've done the same thing except with OR and the right introduction over here. So yeah, basically that. Just give me a minute. So yeah, we can also build true and false over here. within the framework of type theory. So the way we think of this is that true is a type, or I'll start with the proposition version of it first. True is a proposition that has a proof already. So true is something that already has a proof. And false is something that has no proof. It has no terms. And the corresponding types will be what's called the unit type. The unit type is just the type version of this, which has exactly one element. For historical reasons, it's called star, and the star is of type unit. And the type corresponding to the false is the empty type, which has no constructors. There's no way you can produce a term of type empty. So yeah, that's how. There's not much to it really. Like true has a single element or like a single term, and false has none. And why is a specific implementation useful? Well, it turns out it's useful for defining negation. So yeah, these are notations. Yeah, but we can skip over that. So it's useful for defining negation because negation itself in type theory or in this constructive logic interpretation is not a separate type itself, or like it's not given the status of this inductive thing. Instead, it's just shorthand for P implies false. So if you work it out classically, you can find that these two are equivalent, saying that P is false and P implies false. These two are equivalent classically. And we extend this constructively by saying that negation P is true if we can construct a function from type P to the empty type. So basically we want a function that takes an element that takes a proof of P and gives you a proof of empty, which means to say that there cannot be a term of type P. Yeah, so this might have been a little abstract, the negation part. So what I'll do is I will try to quickly prove a simple theorem over here, so that you get a feel for it. So what this is saying is that if I know that P implies Q is true, then I can show that not Q implies not P. So again, this looks familiar classically, but constructively, we have a completely different interpretation of this. So first, to construct a term of type not Q implies not P, what I'll need to do is first assume not Q and then locally construct not P. And with these two things, I can use the lambda thing to construct a term of, basically to construct the function type. So, sorry. So what I've typed out over here is that I'm assuming locally that we have a proof that Q is not true. I'm calling it NQ. And now what you need to fill in over here is a proof of not P. So yeah, so Lean tells me that it's expecting a proof of not P. And not P, as we saw over here, is an abbreviation for P implies false. So not P is P implies false. So lambda. So what this is saying is that, so basically to construct a term of type P implies false, I first locally assume that P is true. And now over here I've left a blank. Lean tells me, at least it's supposed to tell me that I'm supposed to derive false. Wait. Now it tells me that I'm supposed to derive false over here. How do we get false? Well, what we have in our context are, what we have in our context over here are NQ and P. NQ is a function that takes a term of type Q and gives you a proof of false. So it would be good if you can use this somewhere. And you also have P, which is basically saying that P is true. You also have a proof that P implies Q. So you can use a proof of P to produce a proof of type Q. And by putting everything together, so here's what my strategy is going to be. To produce false, I use NQ because NQ promises to be a function that takes in Q and gives you false. And how do you get a term of type Q? Well, there's F for that. F is a function between P and Q. So if I give it a term of type P, it gives me a term of type Q. And how do I get a term of type P? I have one in my local context over here. lowercase p. Now I'll just type a bunch of stuff which corresponds to what I said. It's fine if it doesn't make sense. So nq f, I guess this will work. Yeah, it works. Great. So we produce this term. If we check the type of this term, it will be not q implies not p. And so that means we've proved that not q implies not p with this local assumption that we have a proof that p implies q. So I hope that wasn't too confusing. Yeah, I guess I'm done with this part, the part on logic. So I'll move on. Oh wait, yeah, I need to say a few more things about prop. These aren't really essential details. These are more like more for the sake of completeness. So prop has a special property that any two proofs of a proposition are essentially equivalent. So it doesn't matter to Lean whether basically like any two proofs of a given proposition are considered equivalent by Lean. In a proof, it doesn't matter which proof I use. These are essentially the same. Lean doesn't care. And this is another technical condition which I don't want to get into since it's already past 7. I want to speak about dependent function types, but before that, I'll take questions like about the logic part. Does anyone have anything? Cool, I guess not. I'll move on to dependent function types then. So I'll since it's past 7 and I don't want to exceed beyond 7:30 in any case, I'll try to wrap this up quickly. So yeah, to motivate this thing, consider this example. Let's say we want to construct a function which takes in a natural number n and gives you a vector with n entries. Let's say for concreters, let's say we want to construct a function which takes in a natural number n and gives you the list of the first n natural numbers. So, I mean, this is not too hard to write, but the thing is you also want to encode in the type information that the output is of size n, because this is a fundamental property of the function that you're defining. And it would be nice if these more technical details were captured within the type of the function itself. So within the framework of type theory that we have discussed so far, this is not possible. But if you introduce something called dependent function types, these become possible. So a dependent function type is essentially what I just said. The type of the output depends on your input. So put it more concretely, like it would be good to consider a set theory analogy. So while functions are basically maps from a set A to set B, dependent function types can be thought of as some sort of indexed collection of sets. So you have a fixed set A, and you have a varying family of sets called beta, and where each for each A in alpha, you can produce a corresponding basic. Okay, wait, I'll just put whatever I want to say in simpler terms. So let's say you have an index collection of sets. So the indexing set is alpha, and the index if you pick an arbitrary A in alpha and you look at f of A, then this will have type beta of A, where beta of A depends on A. So this is, as I said, an index family of sets, and we want to capture this in type theory. So that's what dependent function types do. With respect to the actual construction and so on, these are not too different from regular functions. So the introduction and elimination rules are essentially the same. While defining them, we actually make a variable explicit, unlike what we would have written earlier, as just alpha implies t. I'm sorry, yeah, over here we make the variable explicit. Instead of alpha implies beta alpha, we would have just written alpha implies beta earlier. So dependent functions sort of generalize regular functions that we've already seen, and they're implemented in Lean this way as generalizations of regular functions. So was this confusing, or like did it make some sense, like the dependent function type?
Are you saying that the input determines the function also in some sense?
The input determines the type of the output, so it's landing in a different set. So if so for example, consider some map from natural numbers to Rn. So let's say you give me a natural number, and depending on the natural number you give, I'll give you a random vector in Rn. So there the type of your output is depending on your input. Apart from the input itself, depending on your apart from the output itself, depending on your input. So that happens everywhere. But what we're seeing additionally is that the type of your output itself varies with your input. So a function from n to Rn would be a good example.
Right. Okay.
Yeah, that's essentially a dependent function type. And does anyone want to guess what the corresponding logic thing will be? So to give you a hint, what we've seen so far is propositional calculus and or negation and so on. So what do you think these sort of dependent function types would correspond to in the logic version of this? Basically, what's missing from regular mathematics? What symbols are missing?
Some conditionals ID क्या?
No, quantifiers. Like for all.
For
and-
all.
Yeah. So this corresponds to for all because essentially what you're saying is that give me a so if you're proving some property of the natural numbers, say for all n p of n, what you're saying is that give me a natural number, and what I'd give you is something that has type p of n. Remember, propositions are types. So I'll give you something that has type p of n, and p of n varies with n, the input. So this is an example of a dependent type. So universal quantification corresponds to dependent functions. So that's why dependent type theory is so cool. Like you can encode basically quantifiers, and you can extend the regular Curry-Howard correspondence to first order logic as well, like with quantifiers and so on. Why am I? Oh yeah, I think I already said this. So yeah, what I haven't mentioned so far is the existential quantifier. So this notion is a little more nuanced, but I'll still try to explain it intuitively, like even if I don't give the set theory analogy. So when we have some sort of a proposition, like let's say we have a proposition depending on some variable x of alpha. So what I've written over here is x of alpha, p of x. So we have some sort of a predicate sort of thing, like let's say there exists an n such that n is greater than 5. So here n is the binding variable, and the proposition we actually want to speak about is n greater than 5. So how we would go about proving such a thing is by first producing an explicit n for which this is true, and also proving that this property actually holds. And proving that something holds in type theory is the same as producing a term of that type. So basically, again, you have an index family of sets, but instead of giving a function on this index family, what you're giving is something belonging to one of the sets that is being indexed, along with the input from which it is coming. So if I want to speak about this in terms of set theory, basically it's equivalent to giving in the natural numbers to Rn example, it's equivalent to giving some vector of real numbers of finite length and also giving its length. So that would have type that would have it's called a dependent sum technically, but I don't want to go into that. So that would be what corresponds to exists roughly. I don't know if this
like
part,
choice function,
go.
but like a extended choice function. It gives you a thing plus its information or something like that.
Oh no, so for all would be exactly a choice function. So you have an index family, and you're saying for every input you can produce an output belonging to that destination type.
Okay.
So yeah, for all is a choice function, as you pointed out. There exists is more like a dependent sum. So you can think of this as an ordered pair of elements where the second term depends on the first term. So you're sort of taking a disjoint union, but with a huge family instead of just two terms, as we saw earlier.
Right. Okay. Yeah.
Yeah. So that's basically it. So you're essentially taking some sort of disjoint sum. You can think of this as the union with also information of where it comes from. That's the intuition. So that's how you define there exists. Yeah, with that I'm done with this part. I promise I won't take too much long. Now I'll speak about inductive types, which are also like yeah, no, I don't think I have time for demonstrations. So I'll speak about inductive types. So you've seen this sneakily implemented over here in the logic section, where I implemented all these things with the keyword inductive. So we'll see what this inductive actually means. So when I say induction, I guess the first thing that comes to mind is the natural numbers and how you can prove a proposition for all n p of n by proving it for the base case 0 and then proving it for the successor case. So that's why I've decided to start with the example of the inductive type of natural numbers as it's implemented in Lean. So this is all there is to natural numbers in Lean, at least. So what it's saying is that you have a 0 and you have a term 0 of type natural numbers. You also have a function. You also have a term successor belonging to this function type, naturals to naturals, and you're saying that's all there is. So I guess one of the first questions you'll have is that how does this capture everything about natural numbers? What we're used to is Peano's axioms, these 5 axioms over here. But what we've implemented over here is just 2 pieces of information. So the only logical explanation for how we can get from these 2 to these 5 is that we also have some general principles, which is captured by the inductive keyword, from which these 3 axioms trivially follow. Basically, we have generalizations that work for any inductive type. So specifically, what we want to prove is that the successor function is injective. And we also need to prove that 0 is not the successor of any natural number. So we want to come up with a general principle that captures these 2 notions at the very least, and also maybe a third principle that captures induction. So does anyone have any guesses about what general guiding principle could capture 3 and 4? It doesn't have to be very, very precise. Just shoot in the dark. It's fine. Basically, the idea is that you're freely generating the natural numbers from these 2 things. So I'm deliberately being kind of vague about this. So essentially, what it means is that every different expression that you can construct from 0 in the successor function is actually different. So give me a second. So yeah, here's my implementation of the natural numbers. Give me a second. I'll have to go here. Yeah, so if I check 0 is the same thing over here. It tells me that it's a natural number. If I check successor of 0, it tells me that this 2 is a natural number. So we've seen this before, functions and all that. So yeah, let's have a look at this. So this corresponds to 2 in regular mathematics. So how do we know that 2 is not 1? Well, these 2 expressions are different. So we take it to mean that these 2 are actually different numbers. So we assume that these are like freely generated with no additional assumptions or constraints. So yeah, so this is captured in Lean as this thing called no confusion. I don't want to go into it. But no confusion can be used to prove that the successor function is injective, as well as that 0 is not the successor of any number. Or did I say it wrong? Yeah, you know what I mean. Yeah. Right. So with this free generation assumption, we can sort of capture these 2 notions. Does anyone want to have a go at induction, like how we capture the principle of induction from just this information alone? So the hint is that there are 2 ways you can produce a natural number. One is you take 0 itself, which is given to be a natural number in this definition. Another way is to use the successor function to build a natural number from an existing one. So this is what we know, and from this we want to derive induction. We want to state the principle of induction. at least vaguely or heuristically. So do you have any guesses? Like, you can be as vague as you want.
If something holds for like something, and then you have the same thing holding for the suck of that thing. I mean, isn't that just?
Yeah, I mean, yeah, I think,
I
yeah,
mean,
go
it's
on.
the same thing as the actual induction ka thing, right?
Exactly. Yeah. I mean, yeah, basically what you're saying is that you know that there are two ways to produce a natural number. Yeah. And so if you want to prove a property for all natural numbers, you know, the natural numbers can be built in only two ways. Either you start with zero itself, or you apply the successor function to an existing natural number. So these are the only two ways of building a natural number. So if you've shown that a property is true using these two ways, then you've essentially shown that it's true for all natural numbers, for all elements of the type nat or whatever, script n, blackboard, whatever. Yeah. So I mean, I don't want to convey the formal details. Like what I want to convey is the intuition, like how you would intuitively state a principle of induction. And since we're working in type theory, I think it's worth noting exactly what it means to prove a proposition. So a proposition is basically something. It's sort of a predicate where you plug in a natural number and get a proposition, right? Like, so that is, I mean, that's what. So when you have for all n p of n, you need to first specify an n, and then you get the corresponding p of n. So if you say all numbers are equal to themselves for all n equal to n, and you can specify it with the case of 5, and what you get as a result is a special proposition 5 equal to 5. And yeah, so the summary of what I want to convey is that a predicate is basically a function from natural numbers to propositions. It's okay if this doesn't make sense. I'm trying to be a bit more general than I should, because I also want to note the similarity between induction and recursion. So induction is where you take a natural number, or basically take an element of your type, and produce a proposition. Recursion is where you want to build a type. So you take in an element of your type, and you want to build something of some other type using previously built ones. So induction and recursion are essentially the same thing. The only difference is one goes to prop, the other goes to type. That's all the differences. And Lean identifies these two notions. It's okay if what I said didn't make too much sense. You probably know this from regular mathematics anyway, so that's all right. So here's a much simpler example of an inductive type. You have 4 constructors, north, south, east, and west, which are all directions. And to construct a direction, you can just say north or south or east or west. Yeah, so these are basically the examples of inductive types. And I'll try to generalize this in one definition of inductive types. So you can build an inductive type from a finite list of constructors. And in case you're using something like the successor function, which builds in new elements of the type, new elements of the type from existing ones, this should be done in a positive way, which means that you can build only using what already exists. So yeah, this is already, I guess, intuitive. And what I mentioned earlier is that you build things freely. So this ensures that you don't have to prove things like successor is injective and so on. So by the freeness of this. And I guess I've said this already, like induction and recursion are essentially the same thing. Yeah, and yeah, I guess I'll end with this. So that's basically it. And yeah, induction and recursion are the same thing. I've already covered this. Yeah, so I guess that's it. I'll just conclude with what I said in the beginning. Hopefully it makes a lot more sense now that we've got a glimpse into type theory and how things work. Yeah, that's about it. And if you're interested and you want to read more, here are some stuff that I used. This is the manual Theorem Proving in Lean. It's probably the source to go. This is also a very good source, the Hitchhiker's Guide to Logical Verification. Apart from this, if you're interested, I'd highly recommend reading these two blogs. They give a sort of informal and bite-sized introductions to concepts in type theory. So Xena project is run by this professor in Imperial called Kevin Buzzard. You might have seen his name pop up in Quanta magazine articles. Xlane is run by this guy at Exeter. This guy called Gihan Marasinga or something. It's also an extremely well-written blog. So these two blogs talk about induction and all those things in more depth. Yeah, that's basically it. Thanks.